Oh, people are always, is everybody cool with that fact? It's not like, well, what do you mean? There, I can see it's -1. X is not -1. If X could be -1, that would make this 0, but can X be -1? No, so I'm not going to consider it. But there's no more to it than that. So don't feel like, how could we do that? I can see it. No, you're thinking about it wrong. It doesn't say X is -1. It says if X could be -1, then it would be 0. X can't be -1, screw it. So when I go to make my, oh shit, is this G? I don't know. I forget. When I go to make my sign diagram, again, Jeff, shoop, 0. That's it, right? It's undefined here. So you can plug in whatever you want to. Always positive. Always positive for x's we're considering. So this means that this function is always concave up on its domain. Is always concave up, which goes along with this crappy looking little sketch, right? So no inflection points, no yip. Always concave up. So now to graph this thing, I don't know if it's H. This should be, well, yeah, everything's happening mostly right there. Or the 1 was the only real interesting point. -2, right? 0. And now what's my intercepts? How do I get my intercepts? 0, 3. Yeah, you factor this dude. You can take an x to the 1/2 out times x minus 3. So it's 0 and 3. So I do want 3 up there, Jeff. Bam. Bam. This is a min. Now look here. There's an infinite. The tangent line here is infinite. So you just kind of start going. Jeff, you can do it. But screw it. They get the idea. And it's concave up everywhere. So that's neat. This work was difficult, but the graph was almost too easy. You're like, it can't be that, but it is.
For D, after the 0, out of -0 and then positive, you were saying because it's supposed to be a 1, it goes to positive. Why is that?
Oh, here?
Yeah.
Yeah, the 1 came from a root that only occurs once. I really want this. Do you see how that's always positive? Is that cool? So the sign of this is determined by this. Won't the sign of this change around 1? Below 1 is negative, above 1 is positive. If there's a squared or a 4th power or any even power, the sign wouldn't change around 1. That's multiplicity. That's all multiplicity is. It really changes sign because it's an odd power. If it was an even power, it wouldn't change sign. That's it. That's multiplicity. Okay. Yes?
I guess I'm still having trouble like relating the two tests. So you said that, I mean, in the second one, we see that it's concave up and because, I mean, it's always going to go up, right?
Well, no. It can be concave up and going down. Yeah.
Oh, yeah. And you said that made sense because then it agrees with first. So how is, I mean, I guess I'm still having trouble like relating it back to the...
So positive second derivative means it looks like this.
Right. Oh, okay.
Not that it's always going. This would tell me if it's going up or going down.
Yeah.
A positive second derivative means if it's going down less and less and less. If it's going up more and more and more. That's what it means. It doesn't mean it has to be going up. It just means if it's going down less and less and less. To be now concave down would mean if it's going up less and less and less, and starting to go down more and more and more. That's why that ends up being concave down, cup down.
But since there is no inflection point, I mean...
Yeah, no inflection point, so it doesn't have anywhere that it changes to cup down. It just is cupped up always. Yeah, I like it. Some kind of weird take on optimist. Cup up or cup down. Okay. Okay. So last thing for today. always an exciting phrase until you say to yourself, how long is this going to take to talk about? This is section 4.4. That's the one we skipped. We just did 4.3, 4.5 together. They're really the same thing, to be honest. 4.4 is the first place where we talk about L'Hopital's rule. And I love this book because it spells his name correctly. So here's the idea. If I was trying to investigate the limit as x goes to a, let's just start with the most basic one. Yes?
4.4?
Yeah, 4.4. Yeah. And let's start with the most basic indeterminate form. You guys remember what indeterminate forms were? What's the most? 0 over 0 is the most basic. We'll start there. Infinity, no. So 0 over 0 is let's say that this is such that that's true. Which means that the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is 0. Is that cool? Plop, plop, 0 over 0, that must be this. All right, now I'm going to bring in linearization. Oh, shit. Linearization to talk about how to look at this. All right. So remember that from linearization, we got that f of x is approximately, does this sound, remember this stuff? This really is just algebra equation of a line. That's all it is, right? Is that cool? And the closer that x gets to a, the more equal this becomes. You guys remember that part too? Because at a, this is perfect. This would be equal to, wouldn't it? At a, of course it would be equal to, because what happens when you plug an a in? That goes to 0. That whole thing goes to 0. F of a equals f of a. Ooh, it's an amazing statement. So I was going over my head which way I wanted to do this, and I want to be a little more precise. Let's say then that f of x equals f of a plus f prime of a. Let me see if you guys can handle this. Plus some error term. Make it EF to go along with F. You guys remember that picture? Like, here's the curve, and then here's the tangent line. So, of course, the further I get away from that point, the worse the error is. Right? And the closer I get. So the limit, what's the limit as x goes to a of this? How off am I as I get closer and closer to a? This thing is going to go to 0 because, and you can see that here, as you get closer and closer to a, the error is going to go to 0. Because at a, this is freaking perfect. You guys with me still? So I didn't have to introduce this term, but I want to, just so you can see it's going to be in this limit. All right. So the same thing happens with g of x. Is that cool? G of x equals g of a plus g prime of a times x minus a, plus an error for g. Become a little subscript. Now the one, all right, let me stop here. What's up? So don't think too much about this. Okay, does this make sense? The further you get from a, the bigger this adjustment thing is. Right? Because the further I get from a, the more off I could be. So this is how much off I am to make it perfect. Of course, right at a, what is this? 0. So the limit as x goes to a of either e is 0. That's how much when I get to a, how off am I? I'm not off at all. It works perfectly at a. Do you guys remember linearization? What? All right. It's such a long time ago. So real quick. A little review of linear linearization. So if I have a function, let's say, I always use square root. Let's use something else. X squared, right? And I want to linearize this thing at a equal to, let's use 1. So really that just means find the tangent line to this at 1. That's another way to look at it. All the formulas they have in that section 310, I think it is, linearization, are just tangent line formulas, rewritten to look all formal. This shit is tangent line. Isn't that tangent line? What's that? That's y minus y1 equals m times x minus x1. That's algebra shit, right? What's the only calculus up there? F prime of a, which is the slope. Okay, so how to find the tangent line? I got to figure out the slope at 1, so I need this. What's the slope at 1? It's 2. And what's the point? It'd be 1 comma 1. So then I just got y minus the y piece equals m times x minus the x piece. So I got y equals 2x minus 2 plus 1, so I get minus 1. So for values close to 1, this is close to the output of this. So help me out. What's 1.1 squared? 1.21. And when I plug a 1.1 in here, 2 times 1.1 minus 1, 2.2 minus 1 is 1.2. Are those close? Yes. And the closer I get to an input of 1, the closer the outputs will be. That was the idea behind the linearization. Okay. So any function who has a derivative that exists at a point, I can linearize it at that point. Because that means there's a slope, there's a tangent line, that it gets closer and closer to us. You guys see where all this is going? So this is all about getting close to that point. So it kind of makes sense. I should be able to replace these functions with their linearizations, because at A, their linearizations equal the stupid function there. And why is that good? Because then I have freaking lines to worry about, not whatever the shit these functions are. They could be the funkiest ass functions I've ever seen in my life. I'd rather replace them with mx plus b, right? Wouldn't you? I would. I'm going to do it. Right. So let's see what this looks like now. One little extra thing. You're going to hate me for this, but can't I make this x because I'm going to let x go to a? Just work with me. Can't I make this, when I'm going to plug it in here, can't I make this x because x is going to a anyway? Okay, that's the one little piece. That's not perfect. But this is the best non-formalized to hell way I can think of to show you why this works. You just got to go. So if I rewrite this, this will look like this. The top will be f of a plus f prime of x, because I'm letting x go to a anyway. So want to be this eventually? Okay. Times x minus a plus this error shit that's going to go away anyway. Over g of a plus g prime of x, because x is going to a anyway, plus an error that's going to go in. Okay, stay with me. On first blush, you're like, wow, that looks so much better. Just wait. I'm not saying it's going to get better. I'm saying I'm developing a general rule. And then you'll see very quickly that the rule kicks a lot of ass. Anybody that knows L'Hopital, you're like, thank God we got here so I can use the shit out of that thing. Now watch this. Let me see if you guys remember, what is f of a? What's the limit as it goes to a? These are going to be 0. All right, what's the limit of the error function? What did we say? As I get really close to a, how far off am I? 0 off. And what happens to these things? They cancel. So I end up with the limit. Let me just recover. The limit as x goes to a of this equals that. The limit as x goes to a of the ratio of their derivatives. So it really is kind of like, if they're going to 0, it kind of depends on who's going to 0 faster. So if they're both going to 0, who's going to 0 faster, which brings in idea of derivative. So that way, too, it makes sense that derivatives can come into play. All right, let's try this, a concrete example, right? So a concrete example, because you guys are not understanding that the middle shit doesn't mean shit. This is what's beautiful. Look at that, that's beautiful. Now how is that beautiful? Do you remember how funky this limit was? Limit as x goes to 0, sine x over x. Didn't we talk about that before and do all kinds of weird shit with it? Is it in an indeterminate form? What form is it in? At 0, this wants to be 0, and this wants to be 0. So can I use L'Hopital's? Yes. So you cannot apply L'Hopital's rule to anything unless it's in indeterminate form. If you apply it, L'Hopital's like, anything can happen to you. If it's in indeterminate form, it's saying the answer will be the same. So what's the derivative of the top? Because what's L'Hopital's rule say? That this answer is the same as the derivative of the top over the derivative of the bottom. What's the derivative of sine? That's crazy. What's the derivative of x? 1. It's not a quotient rule. You're not taking the derivative of this whole thing. It's the ratio of the derivatives. Not quotient rule. You guys see, that's another mistake I see that people do all the time. Like, this isn't hard enough. Let me make this harder. And when you plug a 0 in, what do you get? Is it still indeterminate? When you plug a 0 in, you get 1. You might remember that that limit was 1. Wasn't that a much easier way to show that? Doesn't that kick like a lot of ass? Yes, it does kick a lot of ass. Okay. So, here, let me show you a couple more and then we'll head out of here. Oh, let's see, what else is kind of funky looking? That's kind of funky looking. The limit. Oh, let me ask you this. If I have infinity over infinity, that's what this is, right? L'Hopital still applies. Because I could actually do the reciprocal, like bring this down reciprocal, bring this up reciprocal, and then wouldn't they both go to 0? If the limit, now watch, let me ask you, if the limit as x goes to infinity of f of x is infinity, what's the limit as x goes to infinity of 1 over f of x? It's not that hard of a question. If f goes to infinity, as x goes to infinity, 1 over f is going to go to 0. So L'Hopital's kind of works. We built it around 0 over 0, but even infinity over infinity, I could rewrite the ratios that would still apply. So I can just kind of attack this anyways. So what are the two main ratios that L'Hopital's works for, the two main indeterminate forms? 0 over 0, infinity over infinity. Those are the types that it works for. So what's the derivative of the top? 1 over x. And what's the derivative of the bottom? 1. So then what's this limit? It's not indeterminate anymore, right? This goes to what? As x goes to infinity, this goes to 0. Bam. And this is interesting. The more you do this, you realize natural log is one of the slowest growing functions there is. So natural log does this. I'm growing so fast, holy shit. Right? So after this point, it's like, it's slower growing than almost every other function. You'll see that if you do enough math. Especially if you get into like 280. Okay, so let's do one more that's in a different form. Let's see if you guys can figure out what to do with this. Oh, I don't want to do that one. I don't want to do that one. Yeah, I want to do that one. That one looks yummy. Get this out of here. Now, this is not a ratio. This is like the subtraction of two things. forms, right? But there are two more indeterminate forms that, in order to use L'Hopital's, I still have to make it a ratio. But what form is this in? At 1, what does this want to do? What's the natural log of 1? What's the natural log of 1? What's the log of any log of 1? 0, because how do you get 1? You raise something to a 0 power. So any log of 1, 0. Okay, so that'll be 1 over 0, which is trying to be infinity. And this will be 1 over 0, which is infinity. Now that seems like it's not indeterminate, but do you see how it matters which one's going to infinity faster? To tell you what. And if they're both going to infinity at like the same pace, maybe the answer is 0 or some finite number. Maybe they're always 2 apart. So as they both go to infinity, the difference is always 2. Do you see what I'm saying? So infinity minus infinity, when you first see, you're like, well, that's 0. What's your problem, stupid math person? But it depends which one's going to infinity faster. Again, that faster thing comes into play. But L'Hopital says, I can't do shit to that. I need one ratio. So how in the world would I accomplish that? Well, I just have to common denominator. Just what's in this thing? It's all gone. So hey, so this guy just needs a it's minus 1. This guy needs a ln(x). So then it can take derivatives of the top and the bottom. Actually, what's happening now? The top here would be 0 minus 0. Do you see that? Over 0 times 0. So now it's 0 over 0. So now it's exactly the one that we built L'Hopital's around. Do you guys see that?
For the lower limit, is it still going
Oh, sorry.
1 from the plus?
Yeah. All right, so now you can attack with derivatives, right? So I get the limit as x goes to 1 from above. 1, 0, 1 over x, right? 1 minus 1 over x. Is that cool? Just take derivatives. And then here, what do I have to do here? Good, this product rule. So 1 over x times x minus 1 plus ln x times 1. Before you start simplifying that, is it still indeterminate? 1 minus 1 is 0. And then 1 times 1 minus 1 is 0 plus 0. Still indeterminate. See that? It's still indeterminate, which means I can use L'Hopital's again. Why would you not want to use L'Hopital's if it was not indeterminate? Well, you're not allowed to. And secondly, why would you? It's not indeterminate, which means you should be able to determine the answer. Okay. So I love when people just go crazy with L'Hopital's. I'm going to keep going until I get a number. Oh my God, no. So here, let's try to simplify this a little bit. What can I do? So I could like multiply top and bottom by x. If you wanted to. Do you see that? Is that all right? Yeah. Why? Because x is going to 1, so x can't be 0, so that's totally allowed. So I got x minus 1 over x minus 1 plus x ln x. And now I can take a derivative again. So what I normally do, what I'm not doing here for some reason is I almost always would put like LH first to tell myself that I did L'Hopital's, right? L'Hopital, by the way, is L hospital. L hospital. It's French, so they have to go L'Hopital. Croissant, not sandwich. I eat for sandwich. I'm American, so with that. We'll take your word and we'll make it American. So if I apply L'Hopital's, I'll get 1 over 1 plus product rule real quick. It would be ln x plus x times 1 over x. Is that indeterminate still? No. Plug a 1 in, that's 0. 1 over 2 is 1/2. Oh, thank God. So before you just blindly apply L'Hopital's after doing it once, make sure you haven't got the answer already. Because not only do you want to stop because you get the answer, but also if you go again, your answer could change. Because L'Hopital's like, I don't know what's going to happen now. Yes?
So when bouncing it, the H and S is silent, right?
Yeah, exactly. So that's why some books I've seen don't even have the S in there.
Okay.
Right, so it's L'Hopital. Right? Yes?
For the step where it says x minus 1 over x minus 1 plus x elements, was that just simplifying or did you multiply it?
I multiplied top and bottom of x.
Okay.
Just to kill the 1 over x shit that I didn't want to do derivatives of. Do you guys see why that is allowed? The only time you couldn't multiply top and bottom of x is if x could be 0, but x can't be 0 because I'm getting close to 1 from above. So I can do that all day, yes?
So all the rules apply except quotient, right?
If I had a fraction over something and I couldn't really simplify, then I would do quotient rule to the top function. But it's the derivative of that function over the derivative of that function. It's not the derivative of this whole function. So very rarely would you use quotient rule. You're going to see the difference. It's the ratio of the two derivatives of the functions, not the derivative of the whole damn thing. Ew. You don't want to do that to yourself. Okay. We've done a lot. We really have, so I think that's good. Yeah, we're pretty good. We're on track. So tomorrow I'll have the practice test, and then next Monday I'll have the answer key, because the test is next Tuesday, right before 4th of July. You're welcome, so you can enjoy that without, well, unless you got homework to catch up on.
So it's Tuesday, not Thursday?
Yes, next Tuesday. Yes. July 3rd, right? That's when I have it? Yes. All right. I am teaching 2 classes, but I think I've got it straight. Yes. Oh, quiz on tomorrow is going 3, 7 to 3. Did I say 3:11?
Yeah.
Ooh, I'm evil. Oh, I like past Jeff. Huh?
You can make it to 3:10.
Yeah, or I can make it to 4:1.
Oh, really?
Or you want us to keep it? You want me to change it whichever way I want to? No? Keep it at 3:73? Okay. All right. All right, guys. It's pretty old. We're get out early all the time.